So we'll do a couple select review questions from your final exam review. And the first one that we'll cover is problem number 10. This one goes over the mean value theorem. And if I remember right, you guys didn't exactly ace this one on the first test, so you might want to try and catch it here. The mean value theorem basically says that the slope of the secant line is going to equal the slope of the tangent line. So let's remind ourselves of a few things here. First things first, they give you the endpoints here, so we'll put in a 0 and 5 into this function. If I put in a 0, I get negative 1 for y. If I put in a 5, I get, let's see, it'd be 30 minus 1 would be 29. And I want to find the slope of that line. So the slope of the line between those 2 points is going to be the slope of the secant line. So how do we calculate slope? Well, that's y2 minus y1 over x2 minus x1. In this case, 29 minus negative 1 divided by 5 minus 0. Isn't that special? It works out nice and even. 30 over 5 is a slope of 6 for the slope of the secant line. Now, the slope of the secant line is going to equal the slope of the tangent line for some point between 0 and 5, at least according to the mean value theorem. By the way, what things have to be true in order for the mean value theorem to apply? Good. The function has to be continuous and differentiable on the interval. So if it has a corner point, like the absolute value, you have to throw it out. If it's discontinuous, again, it doesn't work. But this is a nice smooth polynomial, so we're in good shape on both accounts. So I want to know where the slope of the secant line, m sub secant, which is 6, equals the slope of the tangent line. What tells me the slope of the tangent line? F prime. What's f prime in this case? 2x plus 1. So subtract 1, I get 5 equals 2x, or 5 over 2 is x. So that's the point that satisfies the mean value theorem for problem number 10. We good on that one? Nope, not for this one. We will do one. I think one of the problems you asked did ask for the equation of a tangent line. Let's move on to problem number 13. And here we go. Equation of the tangent line. One thing that I would do to start this, I mean, this isn't that bad of a problem that maybe you want to start by foiling this out. No, foil is actually not the right word because we're going to distribute first of all the x and then the negative 2. So distributing the x, I get these first 3 terms. Distributing the negative 2, I get the next 3 terms. And there's a little bit of like terms that we can combine. Negative x and negative 8x combine and give me negative 9x. So assuming that I did my calculations correctly, which is, you know, a big assumption, let's proceed with finding the equation of the tangent line. What 2 things do we need to find the equation of a tangent line? Slope of the tangent line and the point, right? So the point that they want us to find for tangency is at x equal 1. So let's do this. Let's find the derivative first. So here's our function. Its derivative is going to be 4x cubed minus 8x squared, 6x squared. Thank you. 6x squared plus 8x minus 9 and then plus 0. So, okay, let's clean that up just a touch. There we go, 6, thank you. Now I want to find the slope of the tangent line. So that means putting in 1 into the derivative. So if I put in a 1, I'll get 4 minus 6 plus 8 minus 9, so negative 2 plus 8 is 6, minus 9, negative 3. All right. So that's the slope of the tangent line. Now, if you think back to this equation that hopefully you picked up in algebra, that in order to find the equation of a line, I need a point and a slope, well, I've got 2 out of 3 of these. I've got my slope and I've got the x-coordinate. I need to figure out the y-coordinate. Where am I going to figure out the y-coordinate of my point? Yeah. Not into the derivative function, but into the function itself. So go back to the original f of x, plug in that function, and let's see. We get, well, 1 cubed plus 4 times 1 minus 1, and 1 minus 2. In other words, 4 times negative 1, which is negative 4. So that's our point. Let's keep going here. We've got a point with coordinates at 1 and negative 4. And the slope of the tangent line was negative 3. So I think we can finish this up. It's going to be y minus negative 4 equals negative 3 times x minus 1. Please don't leave it like this. You need to solve for y because I asked for your equation to be in slope-intercept form. So that's y plus 4 equals negative 3x plus 3. If I subtract 4 from both sides, y equals negative 3x minus 1. So that's the equation of your tangent line there for number 13. So far, so good? Okay. I guess one of the biggest errors I see people making is finding the y-coordinate in a place like this. They plug 1 into here and find the slope of the tangent line again, as opposed to plugging it into the original f of x and finding the y-coordinate there. But other than that, that one seems to work out okay. Let's move on to the next one that you asked about, and that's this one. It's part of problem number 18. I actually gave you a lot of these. Now, on the exam, I may not say, gee, do this one by implicit differentiation, but you have to do this one by implicit differentiation. Can anyone tell me what your clue is that, gee, we need to differentiate implicitly? Yeah, you got an x, y. In short, you don't have y solved for. Y is not all by itself on one side of the equation. So let me recopy that and give myself some room. Let me just kind of move up here. So I've got x cubed plus xy plus y squared equals 7. And if you notice, I've kind of written these with brackets around the y, because the y needs special attention. It's not enough just to differentiate the y. You have to differentiate the y terms implicitly. So what's that going to mean here? Well, let me just put parentheses around that term right there, because when we differentiate this, yeah, you got to use the product rule here, right? As simple as it looks, it is still a product. So derivative of the first term, that's pretty easy. That's just going to be 3x squared plus, now let's be careful about this. The derivative of the first term is a 1 times the second, which is a y, plus the derivative of the second. And what's the derivative of the second term there? dy by dx, good. dy by dx times x. Now I'm going to put that x here, even though in the order I said it would go behind the dy dx. And this term needs a little bit of love as well. What rule do I have to use to differentiate y squared? Power rule and something else. And the chain rule. Because it's going to be the derivative of the outside times the derivative of the inside. So for the power rule part of it, it's going to be 2 times y to the first power times the derivative of the inside. There you go. dy by dx equals 0, which is the derivative of that constant. Okay, so there's a couple terms here that have nothing to do with my dy dx term. That's this term and this term. So I'm going to kick those to the right-hand side of my equation. And and rewrite it like this. I'll have x dy by dx plus 2y dy by dx equals negative 3x squared minus y. Getting closer. We want to get the dy by dx term all by itself. So what I'll do next is I'll factor out dy by dx. And there's one last thing to do. Divide. I'm going to divide by this coefficient. I'll finish up with dy by dx equals negative 3x squared minus y over x plus 2y. We've got another one that we're going to do that involves some implicit differentiation, but this is a good example. Okay. Let's move on to problem number 21. Kind of moving our way down your list. So if you wanted another follow-up problem with differentiation, implicit differentiation, you didn't have to wait long. Again, we want to find the equation of a tangent line. This time we want to find the equation of a tangent line to this curve, 4e to the xy minus x equals 0. Don't try trying to get this out of your calculator. It's just not going to happen. You can use nice graphing software like Desmos and things like that to find this curve. If it was something crazy like this, I'd probably give you a graph on the exam. Just FYI, you don't need the graph to solve this. The reason I put it there is so that you can see if your graph makes sense. If you get something with a negative slope as the tangent line, then that's telling you something's wrong. So I'm trying to help you out by giving you that graph. Let's make sure that our equation of our tangent line kind of matches the information we see there. So let's see. I need to differentiate this equation. So d by dx. Let's differentiate that. Oops, other way. Okay, so what happens when we differentiate e to the x? Or e to the sum power? It stays the same, but then we have to multiply by the derivative of the exponent. And the derivative of the exponent here is going to be more than the usual pain. Yeah, you're going to have to use the product rule and implicit differentiation. So it's going to be 4e to the xy times the derivative of the inside. No, what's the derivative of the inside? Well, we already differentiated x times y a minute ago, but it's kind of the same thing, right? Remember, we're going to get 1 times y plus dy by dx times x. But again, I'm going to write that x out in front. But that's just the derivative of that first part. All right, your turn. What's the derivative of this part? The minus x derivative? And negative 1. All right. I'm just seeing if you guys are still awake, that's all. All right, so negative 1. Good. And that's equal to 0. So we got to fuss around a little bit to solve here. Okay. Let's see. How do I want to do this? I'll distribute this term to both of these terms, and I'll move the 1 to the right-hand side. So I'm going to get 4y e to the xy plus 4x e to the xy dy to dx equals 1. All right, let me get that back on frame. This term does not involve a dy by dx term, so I'm going to move that over to the right-hand side. I can't move this over to the right-hand side so freely because it's being multiplied. And to undo multiplication, I'm going to need a division. So it's going to be 4x e to the xy dy by dx equals 1 minus 4y e to the xy. Getting closer. Good. We're going to divide by this coefficient. So writing over here, dy by dx. The screen did, but not you guys. You guys are completely engaged and enthralled, which I like. All right. You're going to tweet about it. So 1 minus 4y e to the xy over 4x e to the xy. And whew, get out the oxygen model. There's our derivative. We're not done. We need to find the slope of the tangent line. Because this problem's a little bit different, because it's involving implicit differentiation, I gave you not only the x-coordinate, but I gave you the y-coordinate. And you're going to need both of them if you're going to find the slope of the tangent line. So we're going to plug in the point 4, 0 into this and see if we can't find the slope of the tangent line. So that's going to be 1 minus, do I have to go farther than 4 times 0? It's going to be 1 minus 0 in the numerator. In the denominator, I'll get 4 times 4 times e to the 0. Right? Because you'll have 4 times 0, just 0 in the numerator, or in the exponent here. So overall, what's the slope of the tangent line? 1 over 16 is m sub tan. All right, last but not least, y minus y1 equals m times x minus x1. It's going to look like this. Y minus 0 equals 1/16 x minus 4, which turns into 1/16 x minus 1/4. So at least the graph has a very shallow positive slope, which is kind of what we would have expected given the graph that we had to start this problem. I mean, the tangent line is not going to be very, very steep here. It's going to be pretty shallow. So something about like this. All right, so we didn't really need the graph, although, like I said, it is a little bit comforting to have the graph. Any comments you would like me to make to wrap up problem 21? Or are we good there? Let's move on to problem number 28. Now, for problem number 28, I wrote this acronym, SOHCAHTOA. What's that all about? Does anyone remember? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent, opposite over adjacent. So, in looking at this one, I'd like to write a problem. I'd like to write some kind of a relationship that involves this angle, this side, and this side. Which trig function can I use that would do that? No. The Pythagorean theorem involves no angles. So it's a good thought. I mean, you're dealing with a triangle. In fact, the way I drew it is a right triangle. Sine. So the sine of theta equals what? 10 over x. Good. And I can rewrite that if I like. Sine of theta equals 10x to the negative first. Or I can multiply it on the other side. But, you know, I think I'd rather keep it here. Because when I differentiate, say, with respect to time, then if I differentiate here, I won't need to use the product rule. If I move that x to the other side, I will need to use a product rule. So let's avoid the product rule. Let's see. I should probably read this. It says fish is being reeled in at a rate of 2 feet per second. What's that 2 feet per second? How would you characterize that in terms of my problem? All right, it's a rate. So, yeah, dx by dt is 2 feet per second. And we're going to do this, we're going to look at this when there's 10 feet above the water. How is the angle changing when there's 25 feet of line from the end of the rod to the water? So x is 25. We'll see where and how we're going to need that. But for now, let's differentiate implicitly. So that's going to be a d by dt. So the derivative here is going to be cosine of theta times d theta dt equals what? What's the derivative of this going to be? Negative 10, x to negative 2. Very good. You still have to differentiate this implicitly. So it's derivative of the outside times derivative of the inside, and you're going to get a dx by dt. So, all right. We need to solve for theta. So, or d theta dt, that's our unknown, the rate at which the angle is changing with respect to time. One of the things we're going to need to know is the cosine of theta. So, okay. Cosine is adjacent over hypotenuse. All right. Well, we don't have the adjacent side. We do have that this side is going to be 25 feet. So how could we find the adjacent side? Here's where we have to use the Pythagorean theorem. So the adjacent side, I'll call this, say, B, is going to be, let's see, 10 squared plus b squared equals 25 squared. So b squared equals 625 minus 100. B equals the square root of 525. So, okay, we've got that square root of 525. And I'm not going to make you factor out perfect squares or anything like that. We're just going to leave it that way. Now that we've got b, can someone tell me what the cosine of theta is? All right, good, b over x. So it's going to be the square root of 525 over 25 times d theta dt equals negative 10 over, let's see, it's going to be x squared. So x was 25 squared times dx dt. Yeah, dx dt is 2. Almost done here. Let's see, that's going to be negative 20 over 625 d theta dt. Now to get rid of this, I can multiply both sides by the reciprocal. So that'd be times 25 over the square root of 525. And there's a little cancellation there. Let's see if we can't clean that up. Yeah, so we're going to get 0.8 or 4/5 times 1 over the square root of 525. There's something that's bothering me about this one still. Is anyone else bothered by our answer here? The units would be in radians per second. Was anyone else bothered by our final answer here? Yeah, that's negative. If you're reeling this in, if it's getting closer, that angle should get wider, right? So why isn't it getting wider? Why isn't it doing what we're supposed to do, or what we think we do? There you go. dx by dt is getting smaller. So that should be negative. When that's negative, that'll make that positive and that positive. And now that looks a little bit more like something that matches our intuition. Is something that, all right, maybe it's getting bigger at a slow rate, but it is getting bigger. This derivative is positive. Dx by dt is actually negative because you're reeling it in. So that length is getting shorter, so that's why we put a sign here of a negative 2. Okay. Any last comments on 28? All right. We had a question on 33. Let me, this problem is very similar to problem number 70 as well. And I've got more room to write here for problem 70. So let's take a quick look at problem 70. If we do this one, problem 33 is very, very similar. So they're both dealing with cones and canonical piles and similar triangles, etc. Okay, so sand is poured onto a canonical pile at a rate of 2 cubic feet per second. Find the rate at which the volume of the pile is changing when the height of the pile is 6 feet and its base is 18 feet in diameter. Now it's important to realize that that's in diameter. So let's draw that, or draw in some dimensions here. And of course this isn't to scale, that's okay. The height is 6 feet. Let's just do a little work like this. What's this distance for this problem? 9 feet. 9 feet, all right, because the problem gave you the diameter was 18 feet, so half of that's the radius, which is what we're going to work with in this formula anyways, which is 9 feet. Now, one of the things that I mentioned here in the statement of this is that you're going to need similar triangles to help you get rid of some of the variables in this equation. And the way that that works is this. In the original problem, you have some height and some radius. So, call it H and R. Now, specifically, in our triangle, we've got a height of 6 feet and a radius of 9 feet. And that gives us a nice little relationship between H and R, because these are similar triangles. So H over R equals 6 over 9. So you're comparing like to like. Now, why do I need that? I can get the height in terms of the radius. So H equals 6/9 times R, and you're probably better off rewriting that as 2/3 times R. So this defines the height in terms of the radius. Nice. Well, what does that do for us? Well, that allows us to get rid of one of our variables in the formula. So let's go all the way back up here. The volume is 1/3 pi r squared h. And I can replace this now with 1/3 pi r squared times 2/3 r. Let's clean that up a little bit. We'll get 2/9 pi times what? R cubed. And that's V. And I hope you can see the nice improvement here. If I were to differentiate this, I no longer have to use the product rule. I no longer have to have expressions around for two variables. All I need is the expression for the one variable. So, Maher, let me differentiate this with respect to t, d by dt. What would that give me? Some help? dv by dt. Good. Now, when we're differentiating with respect to t, t doesn't match this. I have to differentiate this implicitly. So let me put a little box around that. We're going to get 2/9 and pi. Fall asleep again? Man. I think, yeah, it's a signal. It's time to go home. Derivative of the outside times the derivative of the inside. So what's the derivative of the outside? 3r squared times derivative of the inside is dr by dt. Okay. All right, so let's see here. What did they give us? They gave us, let's clean this up a little bit. The 3 and the 9 will cancel. That'll be 2/3 pi r squared dr dt. And that's dv dt. Then what? Well, we can plug in a few things. We know dv by dt is 2/3 pi times, we want to know this when, 9, the radius is 9, and we'll get dr by dt. I think I made a tiny typo in the way I wanted to set this problem up. So it's going to be 2 equals, let's see, 81 divided by 3 is going to be 27. 27 times 2 is 54 pi dr by dt. So 2 over 54 pi is dr by dt. So that's how the height is, that's how the radius is changing. Unfortunately, that's not what I asked for, though. I made a mistake. I probably should have solved for r in terms of h and substitute that in. But let's just finish this one off and be done with it. If I know, what's that? Oh, I could have said r is 3/2 h instead of solving for h in terms of r. The overall problem asks for, where is it? How the height of the pile is changing, at this time. So I should have left h in the problem, not r. So I wasn't thinking through this one carefully. But to finish this one up, dh by dt is just 2/3 of dr by dt. So if I take my answer here and multiply it by 2/3, 54 pi, let's see, I'll end up with 4 over 162 pi. And the units would be in feet per second. So it's not increasing very much at that point. But it makes sense. You need a lot of sand to increase the height when the pile is that big. All right, were I to go back and redo this one, I'd probably just solve for r equals 3/2 h. And then when we got done with our problem right here, we'd be done because we have a dh by dt. But that's not the route we took. But hopefully the answer still makes sense there. Okay, anything else on problem number 70 there? Yeah, what I did here is I differentiated this relationship with respect to t. So that gave me this right here. dh by dt equals 2/3 dr by dt. I took my answer for dr by dt and I substituted in here. So it'd be 2/3 times, what we got up here. And that gave me dh by dt.
But if you had done it where r equals 3/2 h, then you wouldn't have to do the substitution down here.
Correct. Should I'd be happy to go through that if you'd like. Let's just do it. Sorry. We'll get you escort to the parking lot because everyone's going to be mad at you now. So to kind of do this one perhaps the right way, We got V equals 1/3 pi. Instead of R, I can write my expression, Lisa, I can write my expression for H. So it's going to be 3/2 H, and then that gets squared. So that's 1/3 pi times 9/4 H squared times H is H cubed. This will give me a little cancellation. 3 cancels into 9, so I get 3/4 pi times H cubed. And that's V. If I differentiate this with respect to time, then I'm still going to get a dV by dt. This still needs to be differentiated with a little bit of care. This term here has to be differentiated implicitly. I'm not differentiating with respect to h. If I was, I'd just get 3h squared and be done. But I have to use the chain rule. 3 times 3 is 9 over 4 pi h squared times dh by dt. Okay, let's see what we know here. We know dV by dt is 2. I think we're given dV dt, right?
Yep.
Which is the rate at which the volume is changing.
Yeah, but we're looking for the rate at which the volume is changing.
We're looking for. Oh, you know what? It did say.
This is the volume.
All right. So this should be find the rate at which the height of the pile is changing. When the height of the pile is 6 feet and the base is 18 feet. So height of the pile is 6, so 6 squared times dH by dt. So that's going to be 2 equals 9/4 times pi times 36 dH by dt. And let's see here. Cancel in here, 81. So we get 2 equals 81 pi dH by dt. And it, no, there should be a 2 here still, right? Oh, wait. Now that's going to 9. That'll cancel. 9 goes in there, so it's 81. I squared it. 6 squared. 6 squared is 36. Cancel the 4, I get a 9. 9 times 9 is 81, so 81 pi. So I'm off by a constant of 2 someplace. 81 pi equals dH by dt. I'm not sure where I'm off by a constant of 2. Where could I be off by that constant of 2? Where are we missing a constant of 2? 4.
How did you go? Oh,
Squared. 9/4. Not seeing it. Okay. I'm gonna have to repost this part.
9 squared?
Mm,
Is it squared? Isn't it 9 squared? No. Oh, the height. Never mind. I'm looking at the radius.
height of the pile is 6.
Yeah, I'm looking at the radius.
3/2 h by dt. Oh, no, this is fine. Yeah, duh. This isn't lowest terms. So it's just 2 over 81 pi. Whew. All right, good. So this would be still correct. The units would be feet per second. So again, pretty small in terms of the final answer there. All right, let's call it a day here.